Okay, good morning. We are starting today our fourth lesson in this topic, which is unstructured grids, and especially now element-based finite volume method. We were at this point in the last lecture telling that finding the upstream value which enters in the interpolation function for the advection term is very important. And then we discussed that the value of the interpolation at the integration point may depend on the node variables and also of the others integration points, which results in a linear system of equation 4x4 in 2D and 12x12 in 3D. That's where we were in the last lecture. And I was really emphasizing that the concept of donor cell, and I would like to do some comments on that. I'm considering the donor cell what really influences the integration point. The donor cell can be 2 points, as you're going to see now, or 1 point. Can be mixing between a nodal value and an integration point value. And normally, not normally, but many tests in the literature, they call the donor cell is the upstream cell. And then it is, of course, it's okay, because if you are in a 1D problem, I already made some comments on that. If you are in a 1D problem, you don't have any even another alternative of doing the upwind, because the value at the integration point must be this one, and this is the upwind, and at the same time is the donor cell, which gives the information to this integration point. But if you go for 2D, by the way, you are here. And imagine you have, here's the integration point. Imagine you have such kind of flow direction. The donor cell is some point around here which offers and gives the information for the integration point. But many tests, they call the donor cell this point, which is the one-dimensional choice for these multidimensional problems, in this case 2D. Then some tests, they call this the donor cell. They say the donor upwind scheme, but this is the point, which is chosen to be the upstream. I'm not, when I say donor cell, I'm saying the region of offers and influences the integration point. So it's just a matter of understanding, and I would like to clarify that, because you may go to some tests and in a 2D problem they say the donor cell is this one. It's not really the donor cell. It is the donor cell in 1D, you know, but here's the upwind. You choose some upwind point, but it's not really the donor cell. It is the donor cell in the 1D, but here is no longer the donor cell. The donor cell is, in my understanding, is what offers and gives the information upstream to downstream. Just to clarify that in terms of nomenclature, you know. And then I also we saw also this slide, and then the flow comes in this direction, and this is the integration point we want to have the value calculated, the value of phi, let's say, the variable. The donor cell will be this one, if I use, said a normal way to say. Donor cell, in fact, will be a mixing of different points here, no? And then the upwind is here. If you say phi upstream here is this point, you are saying the donor cell, but it's not, this is not the point which is given information. There's some other flow direction which must be considered, and that's what we are going to do now. Find the upstream value, and then this is a scheme developed by Rowe and Schneider. And it's a very powerful scheme to find the upstream value, considering the flow which reaches the integration point, and then you may find exactly the information from where the information comes, and then what gives you positive coefficients. The choice of the upstream value, it's very important in order to avoid negative coefficients, and then negative coefficients, they cause oscillations. And then it's better that you have a scheme which preserves the positiveness of the coefficients. That's of course, yeah. So let's consider one element. This is one element. 1, 2, 3, 4. Divided in 4 sub-elements or sub-control volumes, if you want. When you are looking to the element, this is a sub-element. When you see the control volume, then you say this is a sub-control volume. You know, that just is the same. Let's consider in this situation where you have integration point 1, 2, 3, and 4. But let's consider this condition which you are interested in calculating the value of the variable at this integration point, IP1. IP1. So this point of interest, IP1. And you have a mass flow here entering this control volume, this sub-element, and mass flow leaving. And then in this convention, M.1, which is leaving, is positive, is negative, and this is which is entering is positive. And then let's see this condition. M2 is larger than M1. So the mass flow which crosses this surface S2 is larger, is greater than this mass flow which crosses the surface S1. What that means? That means that the flow, the mass flow which crosses here, part of this mass flow is going there in the subsurface S1, and part is going the other direction. But that's obvious then, that the IP2 point is what offers the information which comes upstream in this point. Therefore, remember the sign here. So minus M2 over M1, this will be greater than 1, because this is greater than that. What means that your upstream value is the phi at integration point 2. But it's physically easy to see. If you now go to the general expression to calculate the value, you will see that phi upstream is phi IP2, so this your value at at integration point 1 is the value upstream with the integration point 2 plus some terms that you want to put some anti-diffusive terms to avoid numerical diffusion. Because if you use upstream differential scheme, so pure upstream differential scheme, you are going to say that the phi at IP1 will be equal to phi IP2 because you are dropping terms here, which really is an antidiffusive flux which tries to minimize or try to reduce a little bit the numerical diffusion that you have if you use that. We already talked about that. But what we see in this picture, that's the donor cell. The donor point is IP2. Offers the full information to IP1, which is our point of interest. Okay? The second case, it's another possibility of the flow, that mass flow is entering here and also comes from the nodal point 2 and crosses the S1 surface. Well, in this case, this mass flow is larger than that and than that, because who is offering, who is giving the information to this point? Part of the information comes from the node 2, and part of the information comes from the integration point 2. So there will be a mixing. The phi upstream is not just one location. It's not this one or not that one. It's a mixing of both points. And this mixing will be done considering the ratio of the mass flow. And then this is the condition. The phi upstream will be dependent on phi, the integration point 2, and also phi 2 is the nodal point. So this we are verifying here that the upstream is dependent on the nodal and also at the other integration point. And then this is one range which is between 0 and 1, because M2 is smaller than M1, of course, because M1 also gets mass from the nodal point 2. Then you find the relation. And what's written here? Let's say if this relation is 0.3, by the way, let's say, 1 minus, because it will be negative, this will be 0.7. So what's telling us that the information which comes to integration point IP1 comes 30% from this point and 70% for this one in this hypothetical relation 0.3, which I just mentioned. So this is the upstream. So when you now go to your, well, the equation, this is here, you go to your equation to calculate your phi at integration point will be your upstream plus, the upstream is here, plus the term. So this is your integration, the value of your function at the integration point. Upstream plus some other anti-diffusive flux that you may find in the derivative that was in the previous slide. If you use upstream differential scheme, then it will be the phi in point IP1 will be the upstream value. So this is one case where the donor's cells are 2 points. Is giving the information for the IP1, and then a third case, which flow comes from the nodal point 2. It divides for the integration point 1 and integration point 2. And then, now, what point is giving the information to the integration point 1? This one only. This mass flow does not carry information from here to there. So that is easy to understand that the information at this point, and in the three cases, our point of interest is here, is to calculate the function at integration point 1. If there is a part of the mass flow leaves through subsurface 2, of course the information comes from 2. So the phi upstream is phi 2, the nodal point 2. So in your equation, calculating your phi at upstream point 1, at integration point 1, is phi 2 plus some antidiffusivity terms that you are introducing. So if you use just a single UDS, you have this equation. I would like to recall that you can do that, then you introduce numerical diffusion. And if you have some antidiffusive flux here, you may reduce the numerical diffusion, but you have to take care in order to have let's say a good term here in order to give the phi at upstream at integration point 1 such a way that you minimize the numerical diffusion and sometimes you avoid negative coefficients. And the negative coefficients you are trying to avoid with this scheme. This scheme, in these three cases that you are dealing with, can be expressed or written in just one equation. Because it was clear in the previous slides that in one case the phi in integration point 1 was dependent of the phi only in IP2. The second case, the phi at IP1 was dependent on phi 2 and also IP2. And the third case just depending on the phi 2. So you can put all together in an expression like that. The phi at integration point 1 is some part of the integration point 2. In the third case, this lambda has to be 0, right? Because then the phi IP1 is just phi 2. 0, so it's phi 2. In the first case, lambda should be 1, because then drops out this phi 2 and depends only IP2. And all the other cases where the relation of the mass flow is here, and the lambda is a function. Lambda is the maximum of minimum recognized in this equation. It's just what I finished. I just talked and I just mentioned to you. If the flow rate is such as that, then you have lambda equal to 1, lambda equal to 0, or lambda between 0 and 1. And what we really have here is a family. It's a family of schemes which gives you positive coefficients. And positive coefficients are important in order to avoid overshoots and undershoots. Negative coefficients may introduce overshoots and undershoots. So this is the region of positive coefficients. It's not just the Rho and Schneider scheme which gives you positive coefficients. Any scheme which it falls inside this region offers and gives us positive coefficients. There is a little picture here, and how you choose different schemes here is based on the way you express the this omega, which is based on this relation. So there's 5 schemes here were studied here. One is the pure upstream, which is this line. The Rho and Schneider is here. There are some others inside here which gives you positive coefficients, but they are different in terms of being a little bit better accuracy in some problems. And this is all discussed in this paper. A family of positive flow-weighted advection schemes for element-based finite volume methods. It's a numerical heat transfer, which is discussed. The family of positive schemes which are flow, we could put mass flow weighted schemes, because depend on the mass flow in order to tell you which point is the donor point, and you can find different schemes. You cannot have one outside of this region. If the scheme is outside of this region, gives you negative coefficient. And this is a very nice discussion which is there in this. Still talking about the advection schemes. This one we just finished, this family, and Ron Schneider, which is the idea of having positive coefficients, in the idea of having the mass flow weighted schemes. This is the only way, is to have the mass flow weighted schemes. This is the only way to have positive coefficients. And then keeping talking about that, I'm going to just explain a little bit about what is inside the CFX for the advection scheme. CFX use this equation, which is that one, only with one beta factor here, because gradient of phi is along the line, is derivatives, you know. So and delta R here is the distance, which is the same as the R, delta S there. And what you recover is here, if beta is equal to 0, you have an upwind, first order. But now you still have to take care about U phi upstream in order to be positive coefficients. Beta equal to 1, and using the gradient of phi as the average of neighboring node gradients, of course it will give you a second order, because you are adding some antidiffusive flux here. That's what you are doing. If you want to use a central differential scheme, I'm talking about what is inside this FX. If you want to have a central differential scheme, you can calculate the phi in the integration point by the shape functions, because central differential scheme, if you say I'm going to use a central differential scheme, in your mind you are already thinking that diffusion terms is the most important, and then you can use central differential scheme. And then if the diffusion term is important, you can use the shape functions for the evaluation of the integration points. So central differential scheme use the shape function. But what's really important here is to have this coefficient as close as possible to 1 because then you have a second order, but also trying to avoid overshoots, undershoots. And then I'm not going to go into these details, but beta is computed such that the higher order possible is used, but not allowing over and undershoots. This is a paper from Barth and Jesperson where they deal with this scheme. What they do, briefly, they calculated around the integration point in the nodes the maximum and the minimum value of the function. And then they calculated the beta such that it's not allowing the phi, the function, to go lower than the minimum and more than the maximum value. So it's a scheme which tries to prevent numerical oscillation and also positive coefficients with this, let's say, simple scheme. It's easy to implement. And this algorithm gives some high resolution scheme, as they say, is to compute beta such that it avoids over and undershoots. If you are with a fixed beta equal to 1, you may have regions of the flow where you have overshoots and undershoots. So what is the technique? Keep beta equal to 1 as much as possible, but not allowing the function to have overshoots and undershoots. And then the value of beta will change for every grid, of course. When you have a very steep gradient in your solution, if you are here in your solution, or if you are here, let's say, if you are here, beta needs to go to close to 0, because this is the it's when a first order scheme can handle that without overshoots and undershoots, but with numerical diffusion. When you are there, you can your beta factor can increase, Such the idea is to put the beta factor as close as to 1, and then you have a second order scheme, but avoiding over and undershoots according to the flow, according to the gradients that you have. So this is the scheme, which is called the high resolution scheme, which is inside CFX. So with this scheme, I think we went through the details of the interpolation functions, schemes which are mass-weighted scheme which promotes positive coefficients. We have all the ingredients now in order to say, let's integrate our equation and let's have a control volume and do some details about the integration of the conservation equations. Of course, we are not going to do all the integration, all the equation development here, but just details, some ideas. Will be not really details, but some brief comments about the integration. And if you reproduce here our equation for phi, we have to calculate mass flow with velocity scalar normal, mass flow, so advection fluxes. We have to calculate gradient of phi scalar normal, which is diffusive fluxes. Source terms, which is easy to integrate in the volume. So what we define here is a normal and the normal is defined like that. Delta y over ds I, j, this is the vector, normal vector. Now everything is 2D that I'm putting here, yeah? Just to be easy to follow. The velocity is components u and v. And how do we calculate velocity scalar n? Is if you do this one scalar to this one, with the ds will drop, it's going to be u delta y minus v delta x, because the delta x is dropped. So it's this one. It's here. This is the flow rate, mass flow rate here. Area is already inside here. This is some kind of a notation that is just to compact the writing of the equation, which says that u1 is u, u2 is v, delta n j, so delta n1 is delta y, delta n2 is delta x. So reproduce this equation, just a notation. I put here just to show that this is used in order to compact the writings. And you already know about contravariant velocity components. And if you remember that u dy minus v dx is our contravariant velocity component without metric normalization. In fact, it's like that. Remember that this is our contravariant velocity components. So, of course, it has to be the same. Is the flow rate is u dy minus v dx, because now in a local coordinate system we are not carrying. So this is the velocity which carries the mass flow, is the contravariant. I put there just for us to remember about the contravariant velocity components. And the calculations are all the same. That's what I put in this slide. Velocity. What are the terms that we have to calculate? Scalar product of velocity and normal. Scalar product of gradient of phi and normal. Scalar product of the stress tensor and the normal and the momentum equations. Scalar product of pressure and the normal. So velocity, gradient of phi, for the x momentum component, the equation, this is like the component which appears in the x component equation. Pressure, I already explained that. It's in a scalar, but if I'm in 2D, and if I want to express the pressure as a vector, it would be pi plus 0j. Then I can do the scalar product, pressure, scalar normal. And then they're all the same, of course. If I have velocity scalar normal is component times dy minus the other component times the x. Gradient of phi, of course, is the component, x component of the gradient, x component, y component of the gradient. Component, x component times the dy, y component times the x. This product is the y component times the other, and the x component times the y component times the x. Pressure is the x component times dy minus the x component with 0, the y component which is 0 times the x. Again, with this repetition of this one, just put in the gamma. So they are all the same. It's always is the scalar product of some variable time with the normal. And then we have here the equation for the momentum equation, which is UI is U, V, and W. The velocity scalar normal, time is the function, it has to come here, then the interpolation function. This is pressure, and pressure is an elliptic variable. Pressure at the integration points, pressure at the integration points can be found using the shape functions. So you cannot do that with the velocity, which is advected, and there is some advection. But pressure in one point, you can use these shape functions to determine the pressure in that point. So it's an easy calculation inside. The pressure in the nodes, you find the pressure at the integration point. This product, and then the integration of this one. This is for the momentum equation, that one for the general equation, which does not have pressure, which does not have, let's say, if phi here is not U, V, and W, then this phi may be temperature, so this is the diffusive flux, heat fluxes, diffused heat flux, advection heat fluxes, you know, source terms, if phi is temperature, if phi is kinetic energy of turbulence, if phi is dissipation of kinetic energy, it also in turbulence, dissipation, now K is the kinetic energy, and epsilon the corresponding dissipation of the kinetic energy. So it's easy, really easy. And now if you can compact this using that notation, previous notation. But what you have to do now is to have here, I think it's, I'm showing the next slide. Now there is another information here that is not ready for the equations, because I have derivatives. I have derivatives of related to x and related to y. I need to get rid of these derivatives. And now enters in the diffusion terms, enters the shape functions. So then here, if I'm going to calculate this term, gamma gradient of phi scalar normal, it is what we showed before, is derivative of phi related to x times dy, minus the other component is derivative of phi related to y. Oh, there was a mistake here. This is dx. This is dx. But how do you find the derivative of phi? Is the derivative of the shape functions, because you are using the shape functions for the diffusion terms. Derivative of n relates to y. But now the derivative of n with respect to x and derivative of n respect to y we don't have, because the shape functions are function of xi and eta. And here comes the coordinate transformation. So we already talked about that. So dn dx will be function of dn the xi and dn d eta. These values we have, because n are a function of xi and eta. But how you calculate this one is the coordinate transformation. We already saw that. And then after you choose your diffraction scheme, everything here is, you know, this is mass flow, it's already known how to calculate the diffusion, the source term. You just put it here what you choose for your advection term. So then you go into the literature. If you are doing your program, if you are creating your own program, you go in the literature and then you choose the scheme that you find better for you, you know. Doing that, you will have then in this case you may have schemes that, in order to find the phi at the integration points, may involve nodal points, or may involve other integration points, so there is the system of equation to be solved. But after that, everything here will be in function of the nodal values at the end, nodal values. Of course, you only can leave some variables inside your equation as a function of your unknowns which are in the linear system. So it has to be here, will be everything, will be, any term will be function of the nodal phi's. And also here, because when you use shape function, will be function of the nodal values. Everything is from the nodal values, so there is the final equation, which is an equation for the contour volume and involving the neighboring points. If you are using an element-based, as we are discussing, your stencil will be like that. You involving the nodal points here, because here's this is already contour volume, you know, but this grid was constructed, let's say this is a polygonal grid, was constructed, let's say, with the triangular elements, you know, and then we will have a system like that, with a stencil like that. If you are not using element-based or some other method, you may involve points which are far from the nodal point, you know, then it's not a kind of what we discussed in the beginning. If it's an element-based, you need to calculate everything inside the element. So the nodal point will be involved are only the nodal points which are related to the nodal where the contour volume is constructed. So it will be the surrounding nodes. You know, if you use some different schemes, then, as I said, then the number of nodes in your matrix, they may change, but they're always the neighboring, because in unstructured grids you can be 5 or 7 or 8 neighboring points. Then you have to solve this equation. Now it's time to solve this equation. It's written there only considering the non-zeros of the equation, but that's the equation you have to solve. This is another matter, another subject, but if you are going to solve the equations only considering the non-zeros, has to be some kind of an iterative solver. Iterative solver. If you want to solve this matrix directly, so then you have to consider all the zeros and also the non-zeros. But we already discussed that in the other course, that we have a lot of non-zeros, a lot of zeros in this matrix. Just a few non-zeros. So it is recommended to use schemes in order to solve the linear system which does not use the zeros, because your storage will be large. Another point, final point, is the pressure velocity coupling, because we are in a collocated arrangement of variables. And then if you are using a collocated arrangement of variables, all variables are at the same point. In this point, you have u, v, here is 2D, né? U and v and p and t and k and epsilon, everything is here. But in order to perform the balances, mass and momentum and energy and everything, remember you have v velocities dot normal, that is the m dot, flow rate. You need the flow rate in those points. And this is what CFX does. Somewhere it's written here. This is what CFX does. But it's a kind of Rhind-Shaw scheme. What is the main idea of this kind of scheme? I'm not going through the scheme, but only the idea. The idea is, I have a momentum equation here. I have another one there, another one there, another one there, and there, and there. The idea, and you already know that from the previous course, the idea is to create a pseudo-momentum equation for the red arrows here in the integration points. Then you can have the velocity at these integration points, which is some averaging of the terms of the equation, which is written there. The average of the terms of the approximate equation. You do the integration, you have the equation for this point, and you do all the integration you have for that, for that, for that. Now you use those equations in some kind of averaging those equations to get, let's say, an average momentum equation at the integration points. That's the idea. What I'm calling here a pseudo momentum equation. So it's an equation which is based on the equation, discretized equations which are around that node, that integration point. And this scheme allows you to introduce in the mass flow the influence of surrounding velocities, and also introducing surrounding gradients of pressure. So when you put this, when you use this velocity to calculate mass flow, all the influence of surrounding velocities and surrounding pressure gradients will enter the equation. Will enter the mass conservation equation, and also the mass conservation equation is used to calculate the other variables, because mass carries all other variables. And then this is the let's say the coupling between velocity and pressure, which is used this kind of algorithm. There are several types of algorithms. It uses this idea. What's not recommended? What is recommended not to just use these two velocities. I could do that, right? It's easy. I have one velocity calculated here, I have another one here. What's the matter of interpolating these two velocities and find one here? This would be the simplest way of doing that. But this does not create the strong coupling between pressure and velocity which is needed for the solution of the equation. That is the reason for not doing that. The coupling is not very well established among pressure and velocity in the region. So you use So it's not recommended just to do the average of the velocities. Well, when you do all the previous steps that were mentioned here, it's time to say how is the approximate equation for the boundary, for the control volumes at the boundary. So control volumes at the boundary, in a cell-vertex method, the unknowns will be on the boundary, over the boundary, the surface. Let's, I will try to do some, I will reproduce that picture just in order to. So if this is our grid, our unknowns are here. If this is the boundary, if this is the boundary conditions are known here. I know if the function is specified, if the flux of the function is specified. So this is my boundary. And according to our the middle of the edge, the center. So I connect here, I connect there, in the middle. Here's my control volume. This element has an integration point here, integration point there, integration point here, integration point there. I don't have the rest of the element. So my other integration point will be here and will be here. It's called their integration point in the frontier, in the boundary. So it will be here, an integration point at the boundary. Another one there. And there. Now you have, let's say phi is temperature. Then you have, let's say you have a specified temperature. Then you already know the values here. You know the temperature here, you know the temperature there, and you. So if the temperature is prescribed, phi is prescribed, you don't need to put those unknowns in the system, right? In the linear system is already, you already know the values. But then what happens? What happens in this case? If you remove these points from the linear system because you already know the value, you are not performing the balance in this control volume. It will be a layer of control volumes in your boundaries. It will be a layer. There will be a layer of half control volumes here that you don't satisfy the conservation principles. And then, you know, it's let's say, goes a little bit away from the previous or the base of finite volume method that we want to have conservation in the full domain. We want to have conservation in the full domain. Not only the interior control volumes, and not having conservation on the control volumes at the boundary, because at the boundary you have a strong driving force of your solution. So there is one way to do that, and let's keep in mind the hypothesis here that our unknown is temperature. If I say the temperature here is T1, and this point is T, well, let's put phi. Phi 2, phi 1, phi 3. Of course, if I have that specified, I know a value of phi here also. Because if I know the phi here, the phi there, the most simple thing that I can do is just to say this is a quarter. This part here is 1/4 of this. And then I can find the phi here. I know also. I can find the phi at the disintegration point, at the boundary. I can find the phi here also, at the boundary, based on these two. Then I can perform, I can do a mass or heat balance, energy balance, any balance I can do for this control volume. And I'm supposing I don't know this value. It will be on my linear system. It will be my unknown. I'm saying I don't know this value, but I know this one, and I know this one. I'm going to do a balance on this control volume, and I will put this equation also in the equation system. And then you will find a value for phi 2. It will be in your linear system. And how you do that? Since you have this value, you can calculate fluxes here. And this one you calculate with the elements, following everything what we already saw. Here also, fluxes, fluxes, fluxes. And these two, I'm doing a blue. And these two, they are found using this value of phi, which I know at the boundary. Then I perform a mass balance here. I put the equation on my linear system, and phi 2 will come out from the solution of my linear system. Then I can check if phi 2 it came out from my linear system, how far or how close it is from my phi 2 which was prescribed. Of course it will be very close to that, and very close to that as much as the grid is refined. But you can see that what I'm doing here, if I'm doing a balance in this control volume, in fact the variable which I'm calculating, let's see if I have another color, is some point here. Because when you do a balance in a control volume, where the unknown is in the center of the control volume. So what comes from your linear system, in fact, is this value. Because I'm doing a balance on this control volume. Of course, if the grid is sufficiently refined, these two values will be very, very, very close. But doing that, doing a balance for this half control volume, what you are doing, you are conserving the properties in all your domain. There is no part of the domain which just the quantities are not conserved. Was it clear? What we do? So if phi is prescribed, let's say temperature as we were talking about, you could leave out of the linear system, but then you don't conserve the properties in this control volume, and the others one which are at the boundaries. But then you say, I'm going to perform a balance. Because I'm applying the boundary condition, because when I'm going to find this flux here, I'm using this specified value of phi. So I'm applying the boundary conditions in this balance, in this control volume. And then remembering that when you do a balance in a region, the variable is inside your control volume, is in the center of your control volume. So what is going to come out from your linear system is some value which will represent the value for this control volume, you know. And then it's possible to have conservation also in a cell-vertex method. When it's cell-centered, you don't have that problem or that question. Because if you have a cell center, your unknown is here. Your unknown, your variable is here. If this is the boundary, cell center, then if you prescribe the value of phi, you know it here. You know it here. This is in your linear system. But in order to calculate the flux here, you will use this point and this point. Of course. It's similar. Because I'm specifying here, I'm calculating a flux which will involve other interior points. Here, I will calculate a flux which involves one interior point, but it's similar. Very, very similar, you know. But your real unknown is not on the boundary, it's there, you know, but it's the same. Here you are performing a balance, but your entire control volume is at the boundary. And here you have a half of it, but it's the same. The point is in the control volume. This point is in the control volume. It's the same, you know. And you can see here suggest some few considerations about if you have no flow at the boundary. If you say the advection flow of any variable, advection flow is the flow rate times the variable. So this is advection of phi. This is diffusion of phi, which is the diffusion of phi, the gradient. But then, of course, no flow at the boundary, and phi is prescribed. So the advection through the boundary is zero, no flow. But the diffusion, there is a diffusion using the prescribed prescribed phi. Second condition, no flow at the boundary, and the flux of phi is prescribed. So again, no flux at the boundary. But now you don't need to do that, to calculate the fluxes, because it's a specified value. And then at the boundary you have already, if you say if it's temperature, you say the flux is 1,000 watts per square meter. Then it's specified. And when you have a flow at the boundary, so it's entering mass on the boundary, then you have a advection through the boundary with some phi specified. You are saying this mass flow is entering my domain, has such specified phi. Then it's like saying the stream of water is entering the domain with 100 Celsius of temperature. Then you have the flow rate. You know the temperatures enter phi. So you calculate this term. In this case, if you know the temperature, you may say that diffusion is zero because you are saying it's locally parabolic. But this is another topic. But these are possible conditions. But this is the important part, to remember that even in a cell center, cell vertex, as in this case, I can have a full conservation. Of course, I'm doing the balance for the half control volumes at the boundary. Nothing new. And how is the solution of this linear system? Now comes what you already discussed. You can solve it for U, for V, for W, for P, for K, for epsilon, for T, and back and forth, several iteratives, several different iterative cycles. There's non-linearities, there is pressure velocity coupling, so if everything is segregated, you need to have some kind of coupling, then depends the solver, but you can solve it in a segregated manner. We already discussed that when we saw cell center, or you solve coupled. But of course, I think I already mentioned that it's not possible, it's not easy, it's not recommended. Sometimes the physics does not recommend it. To try to solve U, V, W, P, K, epsilon, everything in a big matrix coupled. So it will be too much effort in doing that. And imagine if you have multi-phase flow, then you have to calculate saturations and of every phase, and then it's impossible to put all together in a simultaneously manner. It will be too much storage, it will be too large matrices, it will be difficult. So what is done normally is to look where is the most important part when you solve a fluid flow problem. Is the coupling between pressure and velocity. There resides the main difficulty. So let's put this together, U, V, W, and P, to solve simultaneously these four variables, and then the other ones in a segregated manner. And then what results is a matrix like that. We could let's say even write in that you have a, I'm going to put the capital coefficients here, AUV, AUW, AUP, AVU, AVV, A matrices, VW, AWP, AWU, AWV, AWW, AWP, and at last APU, APV, APW, APP, everything here, you multiply by U, V, W, and P, it's equal to BU, BV, BW, BP. This is our linear system. This line is confusing a little bit here. This is the matrix, and when you get this matrix, you want to have all non-zeros here. And this is what they are going to solve. Every entry here is a 4x4 matrix. It's a 4x4 matrix because you have a U1, U2, U3, U4 for every grid. V1, V2, W1 for million grids. P1, P2. So this is the system. And we could write the first equation. In order to have this equation, this is the first one I wrote down. In order to have this equation with non-zero here, non-zero here, non-zero here, and non-zero here, what that means? It means that in your differential equation, you have to have U, V, W, and P. In Navier-Stokes, for the x component of the momentum equation, you have to have U, V, W, and P. For V also. For mass conservation, also. But mass conservation, we know, does have pressure there. And then this coupling, these methods for calculating the velocity at the interface couples and puts pressure inside the mass conservation equation. And then, this is one reason I read when we saw there that I mentioned. This is one reason why the stress tensor, even if it can be simplified, we don't simplify it in the beginning. We leave the terms there. They will drop out automatically when the iteration is performed. But they are there to help those velocities to appear in the momentum equation for x. And they will help for the u and w appears in the v velocity and so on. So what we want to have is all variables and all equations. Then the coupling is okay. There is no problem. It's a little bit more difficult. But if you write the mass conservation equation without having the pressure, this coefficient is 0. Yeah, this coefficient is 0. Because if I'm going to write this equation, will be one term which multiplies the u velocity. I have u velocity in momentum in mass conservation equation. This term multiplying the v velocity. I have a v velocity. I have w velocity in mass conservation equation, but I don't have pressure. It will be 0 times p. You say, can I solve that problem? Of course. Even with the 0 in the diagonal, you can solve. You can solve. But it's better not to have the 0 there. You have a better system of equation if you don't have the 0 there. But solution you can do. You can find it. But it's a little bit more, as much as well-conditioned a zero matrix, it's better, of course.